Cool. So let's start today's discussion. Feel free to ask questions. I mean, you can just unmute yourself and speak out. You don't need to type on in the chat. And okay, so last time we talked about like Gauss's law, whatever Gauss's law, or we call it divergence theorem. We also talk about the Stokes theorem and also their physical intuitions. We know that they actually are the same uh, in from both like a physical intuition and also the mathematical structure. Even though their expression looks very different. So for the Gauss's law, it's like you have a volume integral over some volume. It converts to a surface integral. The surface is a boundary of this volume. Yes. This S, similar to what I said here, is the magnitude is the infinitesimal areal element, and the direction is the normal direction of this surface. And for the Stokes theorem, it's like you have an integral over some open or closed surface. ds. And then this guy is given by the line integral along the boundary of this surface. The boundary of a surface is a loop, right? You can say, so in this integral kind of connects the volume and the boundary of the volume. This integral, this identity connects the surface and the boundary of the surface. So there's another theorem called Green's theorem. We didn't talk about last time, but I think it's good to know it. Anyway, so this Green's theorem is just a special case of those two theorems. So you can derive this Green's theorem from the Stokes theorem. And it's just a 2D version of Stokes theorem. And we know that the Gauss's law is kind of equivalent to Stokes theorem. So we can also get this Green's theorem from the Gauss's law or the divergence theorem. So the first we will show that, and then, so this is the first thing we will talk about. And the second thing we will talk about in this discussion is the condition. So when can we apply this kind of theorem? Yeah, like the assumptions, the conditions.
A quick question.
Uh-huh.
The Stokes, the surface doesn't have to be closed, but all of the other surfaces are closed.
The Stokes, right? This one don't have to be closed, and here the surface is closed because this surface is the boundary of
the volume.
Of a volume, right?
Yeah. Right. Thank you.
Yeah, a boundary is zero, right? Meaning that the boundary of something is closed.
Got it. Yeah.
Actually, this is a very important statement. The boundary of boundary is nothing. It's like this is a boundary. The boundary of a loop is nothing, right? There's no. If the loop is if it's an open line, then the boundary is 2 points, but it's closed, then there's nothing left. Similarly, if the surface is closed and there's no boundary. Okay, so Yeah. So let's talk about the Green's theorem. Okay, so the Green theorem is like okay, so I actually didn't remember this. Uh, so basically, um, like from the textbook, I just copy from the textbook. It's a non-integral. This is a non-integral is equal to a by the way, this is also a closed loop. Um, equal to a area integral. Right. So this loop is the boundary of this area, and this is for 2 dimension. Imagine this is the area we integrate over, and this L, sorry, oops, this L is this L. It's a boundary. So to prove this, we can start from this Stokes theorem. So let's write it again. What's this? Okay, so partial omega dl equal to some omega oops, ds. So let's set this e to be, because you can say we want to kind of identify this line integral with this line integral. So this is nothing but pq0 dot dx dy dz, but in 2 dimension dz is 0. So this is nothing but dl, right? This is nothing but but vector e. So we identify this vector e with this pq0. And like what I wrote down here, this dl is dx dy 0, because it's 2 dimensions, so the third component is 0. And what is ds? ds, remember the magnitude in this case is dx dy, because it's a 2-dimensional integral, like over the R2. And the direction is a normal direction of this region, which is the z hat, right? This is x, this is y. Then the normal direction is the, it's kind of a z direction. Yeah, by the way, feel free to stop me if you have questions. And so this part becomes del e dot z hat dx dy. So this is nothing but the z component of this curve, right? So the z component of this curve, you can work out this guy very quickly by yourself. So this E is PQ0. So the Z component is given by partial XQ minus partial YP. So you plug this result into here. So on the left hand side, you have this guy, like because you identify this guy, E with this PQ0, and this DL is this guy, your dot E with DL. This is nothing but PDX plus QDY, right? And the right hand side is nothing but partial Q minus partial P dx dy. So you can say this is a Green's theorem. So we can prove, we can derive this Green's theorem from the Stokes theorem, right? Is it clear?
Yeah.
Okay, thanks. So it's just a 2D version of Stokes theorem. So for Stokes theorem, we can choose the surface generally like in 3 dimensions. It's a surface in 3 dimensions. But here the Green theorem, the surface is is flat. It's 2 dimension, right? Okay, so of course we can also derive the Green theorem from the divergence theorem. So let's derive the from divergence.
Excuse me. So we like previously we just derived the Green theorem from the Stokes theorem. Okay, I see. Now, thank
Yeah.
you.
Yeah, so here, I just want to make it clear that those theorems are well related. Like Stokes theorem, kind of similar to Gauss theorem, and like in, in like they're actually the same, but at this level, it's difficult to say they're the same. But eventually, if you know more, you will say they're the same. But and the Green theorem is just a special case of the Stokes theorem, and you can derive it like what we derived here. Like what I said, because the divergence theorem is the same as the Stokes theorem, so we should also be able to derive this Green theorem from the divergence theorem. This is what I'm doing here. So we can so how to do that? So let's write down the divergence theorem first. So we have a volume integral dx dy dz, some volume. It becomes the surface integral. So what's the 2D version? I mean, now the volume in 2D becomes an area, right? And the boundary of this volume becomes a loop L. This is L. And E still E, ds. Remember, ds in 3D is the direction is the normal direction of that surface, and the magnitude is the infinitesimal aerial element. So in 2D, the magnitude is the infinitesimal 9 element. So here becomes dl. So let's denote this guy as dn. The reason why, so the magnitude of this dn is a dl. So it's kind of the infinitesimal 9 element, but the direction is normal to this 9. So I denote as dn. So basically the direction is in this direction is dn. And remember dl we used before for um for 9 integral is this vector dl. So basically the dl, we know the dl is dx dy, but dn is a vector that rotates. Assume this is a rotation matrix. We rotate this dl by minus 90 degree, right? So this is let me use another color. So this red vector is a dl, we usually use for 9 integral, but here the dn is a vector that's normal to that 9. So you can say you rotate this dl kind of a clockwise. We usually, because we're using this kind of xy coordinate, we usually say rotate counterclockwise as a positive angle, and rotate counterclockwise as a negative angle. So here is negative 90 degree, right? So what's this matrix? It's nothing but cosine theta minus sine theta and sine theta cosine theta. And so the theta equal to minus 90 degree. And what is dl? dl is nothing but dx dy. Is it clear? Let me know if it's not transparent. We can explain more.
Sorry, we didn't use like this term before, like for the rotation.
Oh, okay. So, so did you prove this Green's theorem using the divergence theorem in the class?
They use the line integral.
You mean you use this Stokes theorem?
No. Starting from the line integral, they proved the Green's theorem.
So they didn't the professor didn't use this kind of approach.
Yes, the textbook didn't. So yes.
Okay, sure. I mean, it's good to know. It's in generally speaking, if you have a vector, let's say this is also, I think this is something you can remember. I mean, I always remember this matrix because it's very important and very useful. So for example, you have a three-dimensional vector, and the component, I can always set up a coordinate such that this vector is within this xy plane, and this vector is called, I call the component ax, ay. Sorry, let's start from the orange. Now I ask you, what if I rotate this vector by angle theta? What's this vector? I call this vector A. This is a vector after rotating by theta angle. What's this vector? What's the component looks like? This is a general question. I mean, the answer is quite simple, like what I said here. So there's a rotation matrix. You rotate this vector by theta angle. This rotation matrix is given by what I wrote down here. I mean, this is always good to know. Sometimes this can simplify your algebra, make your life much easier. So this is nothing but cosine theta ax minus sine theta ay, and the y component is sine theta ax plus cosine theta ay. Basically, you know this is the x component of this vector b. This is the y component of this vector b. You can verify this very easily use some simple examples. For example, I have a vector a, which is 1, 0. Now, if I rotate it by a 90 degree, we know that eventually you will get a vector b with 0, 1, right? So you just apply to this. So this angle is 90 degrees. So this theta equals to 90 degree. Cosine 90 degree is 0. And the minus is minus 1. This is 1. This is what? This is 0. Right? So times this a is 1, 0. This is 0, 0, 1. You get 0, 1, 0, 1. So this result agrees with your intuition. It's a very simple check, right? This is something, yeah, I think it's very useful. But okay, let's back to our, by the way, any question about this part? Yeah, let's back to our discussion here. Okay, so let me erase this part. Right. So this is nothing but minus 90 degrees, 0, 1, minus 1, 0, right? So dx dy. So this is dy minus dx. So we know that this dn is nothing but dy minus dx. and this E. So now we set E to be E to be what? E to be Q minus P. Then the reason why I set to E to be Q minus P is because I want this result match with the Green's theorem on this part. So SA is P dx plus Q dy. So if I set E equal to Q minus P, then this Q minus P dot with this dy minus x, it becomes dx, Q dy plus P dx, right? So this becomes the right-hand side of this integral of this equation. And the left-hand side is the divergence of this vector, which is partial x q minus partial yp, right? This is nothing but this part. So this 2D version of the divergence theorem gave us the Green's theorem. If I set this E to be Q minus P. Yeah, is it clear?
Yep.
Okay, yeah, thanks for the response, I guess. Yeah. Right. So here I just give you two simple derivation for this Green's theorem from the Stokes theorem and the divergence theorem respectively. And yeah. So now I'll tell you two important thing about the condition to apply those theorems. So the first one versus a more tricky one. This one is more tricky. Is about the singularity. So imagine let's first talk about the Gauss's law or the divergence theorem. So let's write down it again. It's dx dy dz. Sorry, it's double integral e ds. So it's kind of closed partial. So now imagine my E equal to R hat R cube. So you can see that very obviously there's a singularity at the orange, right? Like when your R goes to 0, at the orange, this E becomes infinity. So now let's naively apply this magnetic field. So imagine I want to, sorry, let's draw a 3D coordinate. I have a sphere with a radius r equal to 1. I want to apply this divergence theorem to this electron field for this kind of a sphere. So for the right hand side, we can write it down. So E becomes R cube and dot ds. So in this case, because this is a sphere, this is integrate over this sphere, then in this ds, the direction is r hat, right? It's pointing outwards. So it's a ds. Ds becomes r hat ds. So r hat ds. So r hat dot with r vector just give us the magnitude of this vector, which is r. Yes. We know that on that surface, on this surface, all the point, the distance from the point to the orange is 1, meaning that r equal to 1. So it becomes yes. So this is nothing but the surface, the total surface area of this surface of this sphere, which is 4 pi, right? Meaning that the left-hand side is 4 pi. Sorry, the right-hand side is 4 pi. How about the left-hand side? Okay, so let's apply the del to E. So del.
Sorry, I didn't get like the steps between.
Which one? From here to here, or?
Yeah, from here to here.
Okay, so from this step, so here I just so because we are working with this kind of a sphere, so the normal direction is outwards, meaning that it's kind of along the radial direction, which is r hat.
Oh, I mean, what is the r arrow here?
R arrow, okay, so it's just x, y, z. R arrow, like this R vector is x, y, z, like the 3-dimensional vector.
So how it is? What is the connection with the r hat?
Oh, r hat is the unit vector of this, meaning that so r hat is the x, y, z divided by the norm, like the magnitude of this vector, which is square root of x squared plus x. So basically, if you have a vector A, then in physics, I'm not sure about the math, but in physics, I'm pretty sure if you write like A hat, meaning that it's just a vector divided by the magnitude of this vector.
So how do you like multiply the r vector and r hat?
So okay, sure. Basically, it's like you have a vector. Oh, okay. So the physical intuition is like you have a vector A. Let's say in general you have vector A. Now you want to project this vector A onto a direction which is parallel to this, because the direction of A hat is parallel to this direction of this vector A. So it's kind of a project onto this direction A hat, which will just give you the magnitude of this vector, right? The magnitude of this vector is A itself. So for the vector R, for the vector R, the magnitude is R. But this is physical intuition. The mathematical calculation is like you have an R vector, which is X, Y, Z. And you have a R hat, which is X, Y, Z square root of x squared plus y squared plus z squared. You dot them together. I mean, it's just a simple dot product, right? Which is xyz dot xyz square root of x squared plus y squared plus z squared. So this guy dot this guy is x squared plus y squared plus z squared, square root of x squared plus y squared plus z squared. So this is nothing but square root of x squared plus y squared plus z squared.
Oh, so this is just the r.
Right, yeah. Yeah.
And sorry, when you calculate get 1 over r squared, and how do you turn to the 4 pi? And
okay. So this one, the geometric meaning of this one is nothing but the total surface area of this integration region, right? Because ds, remember ds is the infinitesimal aerial element, right? It's kind of a small element. Now you're integrating this small aerial elements over the all.
Oh no, I mean, where is the r 1 over r squared?
Over where's the 1 over r squared? Oh, it's because I say so. This guy is 1 over r squared, but we are integrating over the surface over this sphere, which is r equal to 1.
Oh, I see. Thank you.
Right. Is it clear? Yeah. Any question? Yeah, thanks for asking. Sometimes I just take it for granted. Yeah, hope it's clear now. Yeah, so this is what I'm trying to say. Like the right hand side is 4 pi through this kind of calculation. And how about the left hand side? Left hand side, we only need to calculate this del E first, right? So del E, what is del E? Del E is partial x. Sorry, E is nothing but x, y, z square root of x squared plus y squared plus d squared. Right? So just use the definition. I mean, there's no true. Or I think you can use the the definition of del in the spherical coordinate, but I didn't remember that, so I just I don't want to look up on the internet, so I just use this very basic definition, but it's also quite straightforward actually. So z x squared plus y squared plus d squared. So sometimes the symmetry is very important in physics. So even we do the calculation, we can also make use of the symmetry of this kind of expression. So you can say the first term is this. The second term, to get the second term, we only need to exchange the x with y in the first term, right? For the last term, we only need to exchange the x with z in the first term. So basically, we only need to calculate the first term. Then we can write down the second term and the last term directly. The first term, okay, so I mean, you can do the derivative by yourself. So this is x squared plus y squared plus d squared squared. This guy take a derivative, I get. And the minus x times, take a derivative, you get. Oops, here should be, sorry, here should be, this one is r. The E is r, r over r cube, right? So it should be something like this. But I just need to change this guy, change the exponent. Yeah, right. So here becomes here. Right, so this guy becomes 3 and x squared plus y squared plus d squared 2x plus. So this denominator is nothing but r cubed, and sorry, this is the r6, and this part is the r cubed. This part is like a 3rx squared. So this is for the first term. The second term and third term you can write down plus r cubed minus 3ry squared. Remember, we just replace this x with y. The last term, 3 squared. So you combine them together, you get r to 6 and 3r3 minus 3r x squared plus y squared plus c squared. So this is nothing but r squared. You get 3r cubed minus 3r cubed r6, which is 0. So any question about the calculation here? Yeah, I mean, you can do it by yourself, or you can, I think if you do this calculation in the spherical coordinate, it's much easier, but here I just do it for you in the Cartesian coordinate. Right, the point is the del E through our naive calculation, we get 0. It seems 0 equal to 4 pi. We know that 4 pi is not 0, so it's not true. So why this happens is because, like what I said, there is a singularity at the orange. By the way, from physics, we know that, okay, so I mean, there are 2 ways to fix it. One way, I mean, I think this is the more correct way. It's like, sorry. You assume there's a delta charge at the orange of the coordinate. Basically 4 pi delta x delta y delta z. By the way, this kind of a delta x delta y delta z, we usually just denote as delta r. Right. So if this guy, you can see that this guy is infinity if x, y, z is equal to 0, 0, 0. Otherwise, it's 0. Basically, what we calculate here through this naive calculation, we only calculate this divergence of this electron field outside this orange. We have no idea about the divergence at the orange, this 0, 0 point, because there is a singularity.
I guess there's a 4 pi, right?
Oh yeah, I mean, it's already infinity, so it doesn't matter, right? You mean where should I have a 4 pi? This is
like, yeah.
Right. Here's a 4 pi.
So I think it's not infinity, it's 4 pi, like with the definition of direct function.
I mean, for that function, is delta x. The definition of that function is like this, right? It's 0 if x not equal, is not equal to 0. If then it's infinity if x equal to 0, right? This is a continuous delta function. Of course, for the this delta function ij is 0 if I not equal to j is 1 if I equal to j. Yeah.
And that's just a correction factor for 4 singularities.
Yeah, right. So just to fix this kind of problem, you need to kind of put that function to this del E by hand.
Great. Okay.
Yeah. I mean, if this equality is correct, because physically we know that a electron field due to a point charge is proportional to r hat. Is proportional to like r vector divided by r cube, right? Now we are saying we have a electron field like this. Like what's the charge density? We did a very naive calculation. We get 0, but we know that it's non-zero because there's a point charge.
Right.
Point charge, to capture this point charge, you have to kind of put it. Okay, so it says there's a that function and yeah, like this.
Okay. Yeah. So the equations that we typically use don't work as you get infinitesimally close to the object.
Exactly. Yeah. This is kind of a tricky part. Sometimes you just ignore that and you will feel, okay, so I just do a very naive calculation. I get kind of a nonsense equation, like 0 equal to 4 pi.
You always assume we're some appreciable distance away from an object.
Right. Yeah. So basically, my point is, when you have a singularity, you should be very careful and So this is for the divergence. This is for the divergence theorem. For the Stokes theorem, you have a similar problem. Let's write down the Stokes theorem first, which is what? Always forget. Right. So if I have an electric field, let's use magnetic field. Right. It doesn't matter. It's just a symbol, right? X squared plus y squared. X squared plus y squared. I think it's minus yx. Right. So for this one, if we do the calculation for the if we plug in and do the calculation for the left-hand side, you will get a 2 pi. You can do it by yourself. Okay, so I can do it very quickly for you. So when I choose this partial omega as the circle with the radius r equal to 1, and then it's r equal to 1, you plug in minus y dx plus x dy, which x squared plus y squared. By the way, x squared plus y squared is 1 because we're doing integral on this r equal to 1, right? So this is 1. And this is what? So we can do x equal to cosine t, y equal to sine t. Then this integral is from 0 to 2 pi for t dt, right? So this minus y becomes minus sine t, and the dx becomes cosine t. This is just a standard way to do this line integral. So x is the cosine t, this dy is the d sine t, and this becomes 2 pi 0. This is sine t squared dt plus cosine t squared dt, which is 2 pi 0 dt, because sine t squared plus cosine t squared is 0, is 1. So this one is nothing but 2 pi. So the result is 2 pi. However, like similar to what we have before. By the way, okay, so you can do this kind of a curl of this magnetic field. Do the naive calculation: ijk partial x partial y partial z, bx by bz. Bz here is 0. Yeah, it's a 2-dimensional vector. Then you get 0. Basically, if you plug in, you get 2 pi equal to 0. This is also make no sense. This similarly is because there's a singularity as an orange. You can say when xy goes to 0, the b becomes divergent, right? So so there's a 2 way to fix it. The one way is to, like what we did for the divergence theorem, we say that this is minus y equal to 2 pi dot x dot y.
Is that symbol a z?
Oh, here is 0 because it's a 2-dimensional vector, right? So
I mean that c with that z with a superscript of 0 on the left there.
You mean where?
The thing that you would use to just on the left at the bottom here.
I mean, which part?
Left del. Yeah.
Del, right? Del cross b equal to 2.
Yeah, left of that.
That's 1.
That just means 1.
Oh, yeah.
Oh, thank you.
So 1. Yeah, whatever. So this actually makes sense because if you draw your magnetic field is kind of circulating like this. You know that if you calculate this the curl, you should get a non-zero value. But you get zero value because there's a singularity. And to fix this, we need to restore that function at the singularity point. At a singular point. So here, so the physical situation, like physical interpolation for this is like there's a current, there's a wire through the orange, like pointing in the z direction. The wire is along the z direction through the orange, and this wire will provide like this. A current will give us a circulating magnetic field. So if you calculate this B outside the singular point, you will get zero because outside that region there's no current. But this calculation only capture the current outside the singularity. So to kind of capture this current at the singularity, we need to restore this 2 pi delta function by hand. There's no way to fix it other than putting it by hand.
So just a quick question.
Sure.
I don't understand why curl calculation del plus A gives the picture outside of the singular point, not inside.
Okay, so that reason is very tricky. I can tell you. So basically, so you can see the del calculation depends on this kind of derivative stuff like that, and this kind of derivative is well defined if there's no singularity. If there's a singularity, even the some function is not well defined. You cannot take a derivative at a singular point. Meaning that if you do this kind of calculation, it contains no information about the singular point.
Okay, okay.
Right. I mean, whenever there's a singular point, it's always tricky in physics.
Okay.
Yeah. The reason why this kind of non-integral give us the correct answer is because it's a non-integral. There's no integration over the singular point. It's an integration along the circle, right? There's no singularity on the circle. Right. Another way people usually say, okay, the Stokes theorem only applies when the region is simple connected. When I say simple connected, like very roughly speaking, meaning that there's no singularity. So simple connected meaning that there's a rigorous definition, simple connected region, meaning that you draw an arbitrary loop. This loop can be shrunk to a point. So if there's a singularity, if you draw a loop enclosing this singularity, there's no way to shrink this loop to a point because there's a singularity preventing you to do that. If there's no singularity, you're free to shrink this loop to a point. It's simple connected. This is what we mean by simple connected. So people usually say, okay, Stokes theorem only applies when the area like the region is simple connected or something like that. And yeah. But if you really understand it, you can restore this kind of function you lost when you do the del calculation, and then it works for all the regions. So I think those two examples like I give here, like this kind of a B field minus yx divided by x squared plus y squared, and another electro field, which is kind of proportional to r vector divided by r cube, are two common examples that's like sometimes actually since I taught last quarter like this class, they actually give like an exam problem about this, like ask you why this Stokes theorem doesn't work for this field. Yeah, it's because this kind of a del calculation breaks down at that singular point. The reason is quite simple. Any question about this? I think the time is up. You are free to go if you have no question. If you have question, you can stay here and we can discuss. Yeah, let me stop recording first.